Welcome back to another lesson in MCV4U. Today we'll be looking at algebraic vectors in R cubed. And so the collection of all the real numbers in three dimensions is known as the R cubed space, or again, uh, three space. And R cubed space includes the XY plane, which we saw was included in the R squared, or the two space, but again also adds this depth of the third dimension, which we represent as Z. So here again, all vectors in the R3 space, R cube space can be expressed in both component form and standard basis form. So again, we're just adding an extra third dimension or depth of Z here. And so it means that in terms of our coordinates, again, we don't just have X and Y, but we also have Z. So again, in component form, if we have this vector, we have vectors equal to A, B, C, or again, we can write it in the that's the coordinates, or we can write it in the component form, which is vector v is equal to a, and b, and c. And so here, when we look at our standard basis form, and we have our vector is equal to a times the unit vector I plus b times the unit vector j. So this was the same as what we saw in same as in two space, or r squared. Again, but here we're going to add, again, plus c times the unit vector k. So here, this is added in our cubed. Okay. So note, now there are three reference vectors. So unit vector I, unit vector j, and unit vector k, which are, again, unit vectors in the direction of x, y, and the z-axis, respectively. And you can see the diagram that's provided on the right. So again, similarly to vectors in R squared, or two space, the magnitude of the vector v is equal to a, b, and c. And then in R cubed can be determined using the formula. So remember when we looked at it in squared or two space, our magnitude of our vector was equal to square root a squared plus b squared. Again, and we represented that by using the Pythagorean theorem. And similarly here in three space, our magnitude of vector is now equal to the three, again, components that we have squared. So here we have the magnitude of the vector is equal to square root a squared plus b squared plus c squared. Okay, so let's look at this first example here. It says consider the vector a is equal to negative I plus 3j minus 2k. So that's in our standard basis form. And it wants us to write, again, it in component form. So we want it to go from standard basis form to component form. So here, vector A is equal. So again, we look at the scalar in front of each of these unit vectors. So in front of I, it's -1. In front of j, it's 3. And in front of k is -2. It means our x value is -1, our y value is 3, and our z value is -2. So here it wants us to find the magnitude of the vector as well, and so we can use the formula that we see up top. So a squared plus b squared plus c squared. Here our a is -1, our b is 3, and our c is -2. So we have square root -1 squared plus 3 squared plus -2 squared. That'll give us an answer of square root 14. Okay, next we'll look at adding algebraic vectors in R cubed, or three space. To determine the sum of two algebraic vectors, add their corresponding x, y, and z components. So here, for example, if vector u is equal to a, b, and c, and vector v is equal to d, e, f, then vector u plus v. So again, we're adding up here the components again for the corresponding x, y, and z values. So in vector u, again, the x value is a, and in vector v, the x value is d. So a plus d. Similarly for the y values, in vector u, it's b, and vector v is e. So b plus e. And then finally, for the z values, again, c plus s. And so then if we look at u minus v, so a minus d now, b minus e, and c minus f. Okay, so example 2 here says for the vectors, vector a is equal to negative 2i plus 5j minus k, and vector b is equal to 2, 0, negative 3. Determine a plus b. So here, again, if we write our a value here in our vector a in component form, we see that negative 2, 5, and negative 1. And here we'll write our vector b in component form, which will be 2, 0, and negative 3. And so here we see that vector a plus vector b will be equal. So again, the corresponding x values in both vectors, so negative 2 plus 2, 5 plus 0, and negative 1 plus negative 3. Or again, negative 1 minus 3. And so here, look at 0, we evaluate 0, 5, and negative 4. And so vector a plus b is 0, 5, and negative 4. And so that again is in component form. If we did want to convert it into standard basis form, again, we would see that again, vector a plus vector b would be equal to, no I values because it's 0, be equal to 5j minus 4. Okay. Okay, so here for b, we have vector a minus b. So here, vector a minus vector b is equal. So again, we have negative 2 minus 2, 5 minus 0. Those are the y values, and negative 1 minus minus 3. So here, when we evaluate it, we'll get negative 4, 5, and 2. So again, this is in component form. This one was in standard basis form. And so we'll do the same thing again, just so we can see it in this situation. So therefore, vector A minus vector B in standard basis form would be negative 4 times unit vector I plus 5 unit vector J plus 2 and the unit vector. Okay. Okay, so example 3 says given vector A is equal to negative 1, negative 2, 0, B is equal to, vector B is equal to 0, negative 2, negative 3, and C is equal to negative 1, 0, and 2. Find the vector D, which is equal to vector A minus 2 times vector B plus 3 times vector C. So here we can write it. So we'll write vector D is equal, again, to A, and we know that A is negative 1, negative 2, 0, minus 2, vector b, which is 0, -2, -3, plus 3, -1, 0, and 2. So here, and write it as one big component form. So here we have, we'll do the x values for both, again, vector A, vector B, and vector C. So here we have -1 minus 2 times 0. So really what we're doing is just expanding here in terms of the x values, plus 3 times -1. The y values, we have -2 multiplied by, again, our negative, so it's +2 minus 2 times -2 plus 3 times 0. And finally, for our z values, negative times 0, so just 0, minus 2 times -3 plus 3 times 2. And so here, vector d will be equal to -4, 6, and 12. And that's in component form. And so in standard basis form, it'd be -4 I plus 6 j plus 12. Okay, so here we'll look at algebraic vectors defined by 2 points. So again, if a vector has initial point of a, x1, y1, and z1, and a final point of b, x2, y2, and z2, then the vector AB will be equal to x2 minus x1, y2 minus y1, and z2 minus z1. And therefore the magnitude will be equal to the square root of a squared plus b squared plus c squared. In this situation, a squared is x2 minus x1 squared, and then b squared is y2 minus y1 squared, and c squared is z2 minus z1 squared. So here, if we look at the example, it says if a is equal to 3, -1, and 5, and b is equal to 0, 2, and -3, determine, again here, vector AB. So here, vector AB is equal to 0 minus 3, so -3, 2 minus minus 1, so 2 plus 1, which is 3, and -3 minus 8, which will give us -8. And so then the magnitude is equal to square root our components, so -3 squared plus 3 squared plus -8 squared. So that is equal to 9 plus 9 plus 64, which is equal to square root 82. Okay, the last concept we'll look at in this lesson is sketching vectors in our cubed on 3 space. So again, every point in 3-dimension space is assigned coordinates A, B, and C. Similar to when we look at things in 2 dimensions, we're always assigned, again, an X and Y value. A position vector can be drawn from the origin to the point. Again, if we go A units in the X direction, so again, A units in the X direction, B units in the Y direction, and C units in the Z direction. The numbers A, B, and C are called the components of vector OP. Okay, so again, if we look at this diagram, again, so in the following diagram, the points P, the point P is 6, 2, and 4 is located in 3 space R cubed. What are the coordinates of A, B, C, D, E, and F? Okay, so here, if we look at the A value, okay, so here we see that. And if we look at the origin, let's put the origin in green. Again, we see that here, the point is at 6, 2, and 4. And here it is the vector point coordinate A, or the point A, lies only on the lies only on the x-axis. And so the coordinate for A would be 6, 0, and 0. Here, if we look at B, so here again, it moves first, again, the same thing, it moves 6 units on the x. So it moves 6 units on the x from the origin. But then here it also moves 2 units on the y as well. So here we see that the coordinate for B would be 6, 2, but it's still flat. So again, it doesn't move on the z axis. So 6, 2, and 0 would be our B. For C, again here, we see that it moves, again, from the origin. So it moves from the origin to a certain point. So it moves from the origin to that point, again, which is 6 in the x. And then now it doesn't move anywhere on the y, but it does move on the units on the z, which would be in 4. So here, our C coordinates would be 6, nothing on the y, so 0, and 4. Okay, so then we look at D. So if we look at D here, again, it starts at the origin, doesn't move any units on the x-axis, doesn't move any units on the y-axis, but it does move the units on the z-axis, which is 4. So here, for our coordinates for D are 0, 0, 4. So look at E, again, doesn't move anything on the x, doesn't move anything on the x, but then moves, again, units on the y. So that would be 2 units on the y, and it moves the 4 units on z. So again, for E, no movement on the x-axis, 2 units on the y, and 4 units on the z. And then finally the F here, again, no movement on the x, only moves the y, and no movement on the z-axis. So here, again, it would just be 0, 2, and 0. Here it just tells us to draw the vector OP. So it would look like this here. So that'd be the vector OP. Okay, so example 6 says the point T, which is 3, 2, and -4, is located in R cubed or 3 space. Draw the vector OT and using our prism method that we looked at up at the top as well. Okay, so here, again, when we look at it, so it moves 3 units. So here we'll just kind of label this, so 1, 2, 3 approximately. So again, use 3 units again on the x. So 1, 2, 3. It moves 2 units on the y. So 1 and 2, approximately. It's not going to be exact here. Okay, and then it moves 4 units down on z. So here we just go 1, 2, 3, 4. So approximately point B will be here at 3, 2, and -4. Okay, so here we can complete our prism. So just represent that using the dotted lines. And so it'll look approximately something like that. Okay. And here, example 7 says plot the point P is equal to -1, 3, and 2. And again, it says to draw the vector OP here as well. Okay, and so here, again, if we plot this point, again, -1, 3, and 2. So here, if we look at this here, again, it moves -1 on the x, -1. It moves 3 units on the y, and finally it moves 2 units on the z here. Okay, so that's our point. -1, 3, and 2. So here we draw our prism. I should use a different color here. So draw our prism here. Okay, so here we have our prism. Okay, and so here, if we look at, again, some of the vertices on the prism, again, here, if we look at this point, for example, that I highlighted in the green dot, again, it moves nowhere in the x, moves 3 units, again, in the y, and then it moves 0 units in the z direction. So here would be 0, 3, and 0. Here, this point here, again, doesn't move in the x, doesn't move in the y, but moves 2 units up in the z. So here would be 0, 0, 2. Here again, this here is our origin. So that's at 0, 0, and 0. Here, if we look at this point here, again, moves 1 unit. Again, 1 unit negative on the x, moves 3 units on the y, but doesn't move on the z. So here, this would be again, -1, 3, and 0. This next point here, or this next vertice, again, doesn't move on the x, again, moves 3 units on y and moves the 2 units on the z. So here, this would be 0, 3, and 2. So looking at the last few points, so we'll look at this one here. Again, moves -1 units on the x, doesn't move on the y, and doesn't move on z. So here would be -1, 0, and 0. And finally, our last vertice here, again, moves 1 unit, -1 units on the x, doesn't move on the y, and moves the 2 units on the z. So here, this would be -1, 0, and